Assalamu alaikum. This is Dr. Usman Paracha, and we are now going through lecture number 11 of the subject Applied Quantitative Analysis and Practices. Just to have a recap of a previous lecture, we just had a detailed discussion and a practice on scatter plotting, how scatter plots are used in SPSS, how this technique is affecting our analysis, and how much this technique is effective in giving us more detailed information about the relationship between two variables, or even more than two variables. So therefore, this tool basically is mostly used to have an overview of the relationship between two or more than two variables before commencing to any detailed analysis. So that's why initial observation or initial review is important, and in this case it's an important facility and tool available in statistics and again in SPSS as well. So we went through the different methods through which scatter plotting can be done, and after that the two most important quantitative measures were discussed in detail. First one is covariance, and covariance basically is used to express the relationship of two variables, but as compared to scatter plotting, of course, scatter plotting just gives us a graphical review of the nature of relationship between various variables. So, but as compared to that, covariance gives us a figure, it gives us some intensity scale in which the relationship between these two variables can be measured effectively. However, there are issues with covariance, as we discussed before, that it hasn't got any specific unit, and then again it has got certain issues in this case, because we cannot compare the measure of covariance with other covariance figures which are presented from any other study. So coming to this point, again this is very much important, that the second important I would say factor which is used to measure the relationship is coefficient of correlation. It's a more refined form of covariance, and again it gives us the intensity of relationship on a certain scale, and the advantage of that coefficient is that this figure can be easily measured and compared with any other coefficient of correlation determined from any other study. So that's why coefficient of correlation is used mostly in and is reported commonly in the studies, in addition to other advanced basic figures of other statistical analysis. So we just had a brief overview of the application of these two quantitative measures in SPSS. So going through that, then afterwards we switch to the features. Again, the population coefficient is termed as rho, and the sample coefficient of correlation is termed as R. Now both features are a bit common, they're unit free, the range in between -1 and 1, then again the stronger is the relationship if the relationship is closer to -1 or 1. However, the direction of the relationship depends upon the sign. For example, in case of a positive sign, it means that figures amounting closer to 1 would portray positive linear relationship, and in case of negative sign, the figures which are closer to -1 portray a stronger negative relationship, and then again 0 is a sign of no relationship at all. So now basically what we know about is that, okay, fine, the correlation coefficient ranges in between -1 and 1. 0 is no relationship. However, the distribution of the effect size, or in this case, is that plus or minus 1.1 is equivalent to small effect, and then again plus minus 0.3 gives us medium effect, and then plus minus 0.5 or larger is large effect. So based on this coefficient of correlation, which is represented by R, if we take the square of this R, we then end up with another coefficient which is called coefficient of determination, and again this R square basically gives us proportion of variance shared by other variable, and gives us a very important information regarding this, that what's the intensity of variance which is being shared in between these any two variables in this case. So then there's an issue that there's a third variable problem, because whenever we are reporting the coefficient of correlation, it does not give us additional information about the impact of any other third or fourth variable which may have a part in the relationship between these two as well. So any of these two variables may be impacted by a third or fourth variable as well. But of course, as we have not taken that into account in this analysis, so the possibility of the presence of other variables remains there, which may impact this relationship between these two variables, which for now we just had in view. Then the second issue related to that is with the causality, because correlation will not tell us anything about which variable is basically causing the another. So it can be that the first variable may be causing the other variable, which is a second variable, or it may be the opposite, that second variable may be causing the first variable. So it can go in either direction, but coefficient of correlation in basic fact will not tell us exact detail of that direction of causality. So this is one of the drawbacks of correlation in this case. So then correlation has got many types basically. Here basically two types are being mentioned, which one of them is Spearman's rho, and the second one is Kendall's tau, and the first one, which we primarily discussed before in our previous lecture, was Pearson correlation. So there's a difference between these two, as you can see in SPSS. Let's say going to the file of in which we are observing the relationship between the exam score of students and the anxiety experienced by them, and the time which they spent in revising the material. Now in this case, when we just tried to find out the correlation coefficient, we just clicked on analyze and went to correlate, and we basically selected bivariate here. Now here you can see that in bivariate correlation we are asked about three correlation coefficients. One is Pearson, which we discussed now. Then the second is Kendall's law, and then the third is Spearman. Now these three are different in nature. So Pearson correlation coefficient is used when we are trying to analyze the interval ratio data, and both the variables comprise of that. And then again Spearman basically is used when one of the variable is ranked variable or ordinal variable, and likewise Kendall is also used for the same purpose. But the difference between these three is portrayed here. As you can see that Spearman's rho Pearson correlation here is based on ranked data, and then again the Kendall's law is used for small samples, not for large samples. So that's the basic difference between these three types, which can be used for calculating the correlation coefficient. So then you must have noticed that going to the previous analysis, we went to the analyze button, and then when we clicked on correlate, we were asked to click on either bivariate correlation or partial correlation. So bivariate relationship is purely used to find out the relationship between two variables, and in this case you see there's another option available which is also called partial correlation. Now partial correlation basically is used to measure the relationship between two variables while controlling for the effect of third variable. Now in this case specifically, as we discussed before, that there is one drawback of correlation, that it may not give us exact detail of whether a third entity may be impacting the relationship between two variables whose correlation we are trying to find. So in this case we can use this tool of partial correlation, and in order to do that, let's take an example here, and just going through the SPSS before, let's have a look at the previous analysis. We just basically were observing the relationship between these primarily variables like time spent on revision of variables, then exam score, and then the anxiety felt by the students. So let's say we just try to find out the relationship between these three using correlation, and we click on OK. So now here we can see from the results that the Pearson correlation between time spent revising and exam score is 0.397, and that of the time spent revising and exam anxiety is negative 0.709. Now here this is giving us a brief introduction of the relationship which may exist between these variables. Now if we take the square of this R, it would give us the variance basically between these two variables. So let's say if we just square this value 0.397, then the square of this value would give us the variance which is existing in between time spent revising and exam performance. And likewise, if we take the square of exam anxiety with time spent revising, then it would give us information about the variance which may be existing between time spent revising and exam anxiety. So this squaring of option gives us some very additional information. For example, let's take the square of exam anxiety and time spent revising. So let's go to compute variable here, and in fact, no, I think this won't be advisable here because we cannot use the calculator option here. But going to the calculator option here, we can see that the square of 0.709 0.709, now this is 0.5. Now this tells us that these two variables have got 50% variance common in between each other. That's in between exam anxiety and time spent revising. And likewise, the variance in between the other two variables with each other can be found out by taking the square of the correlation coefficient. And again, as we have discussed before, that by taking the square in between of the value in between these two would give us coefficient of determination, which again gives us the variance figure. So coming to our scenario here, in case of partial correlation, basically here let's consider a case in which let's say here in the first step, you can see right here, you can see here in first step the correlation between exam performance and exam anxiety as portrayed here in this screen. In between these two, we tried to find out the correlation, and when the correlation figure was squared, we were given the variance accounted for by exam anxiety, and here it's the variance accounted for has been reported to be 19.4%. Now this variance is being shown here in this basically square, which is or rectangular shape, which is common in between these two. So now coming to step 2 here, we can see the correlation issue between exam performance and revision time, and if we square the correlation coefficient, we can see that the variance accounted for by revision time here is 15.7%, which is being showed here by this common area in between these two. Likewise, then we in step 3, now this is evident that if we combine the three variables here in this diagram, we can see that there's a unique variance which is being explained by revision time, in exam performance, which is being shown here in this part. However, the unique variance accounted by the exam anxiety is being shown here in this box. However, all these three variables intersect each other, which is a kind of a common variance which is being explained by exam anxiety and revision time equally. So here in this case we have little idea whether how much impact this third variable is having on the relationship between these two variables like anxiety and exam. Here you can see from this diagram here, in this case the relationship between exam and anxiety is being found out from the correlation coefficient. However, there's a third variable which is impacting and has a relationship between both of these two, and which would have an impact. So what would be the real relationship between these two main variables like exam and anxiety if the effect of this third variable called time revision is controlled? So if we are able to control this third variable impact, then we will be able to know the exact amount of relationship which would be existing in between these two main variables. So going to this fact, let's go to the main SPSS diagram. Let's see how to calculate this relationship in SPSS. Let's say I click on Analyze button and I click on Correlate, and I select partial correlation. So I just am interested in trying to find out the relationship between these two independent variables which are stated here. Like one is exam performance, the other is exam anxiety, and I want to control the impact of third variable which is time spent revising. So I click on it and I click on the arrow under the controlling for dialog box. So by clicking on it and controlling it, let's click on the options, and here we are more interested in zero order correlation, because in this case if we click on zero order correlation, it would tell us the result of the bivariate correlation coefficients as well, so that we can compare these various relationships. We can compare the bivariate correlation coefficients with the partial correlation coefficients in order to have a more clear picture of the nature of relationship in between these variables. So I click on Continue and I click on OK. So here you can see that in the first box, in which we are being given the relationship between these three variables like exam performance, exam anxiety, and time spent, and we have not controlled any variable at all. So we are given the conventional correlation coefficient figure, which we have obtained before. For example, you can see the relationship between exam performance and exam anxiety is 0.441, and in fact it's showing a negative relationship. Now here the relationship which is being described here is not taking into account any third variable, which may be time spent revising. So coming to the next window, which in the last two rows, in there you can see the time spent revising has been included as control variable, and when we include this variable as a control variable here, we can see that the relationship between exam anxiety and performance has been reduced to 0.247. Now initially this was 0.441, and now it's reduced to 0.247. That means that in actual sense the relationship intensity between exam anxiety and exam performance is lower if we control for the effect of the third variable, which time spent revising. So that means that the above mentioned bivariate correlation coefficients are not basically giving us a true picture between these variables. So in order to have the true picture, we just went for partial correlation, and here you can see it's easy to see that 0.247 is the real figure. But in order to go into details, let's account for the variance cost, and here let's say if I take the the figure 0.441 and I take its square, then it's 0.194. That means that the variance accounted for in between exam anxiety and exam performance was 19.4%. However, in this case you can see when the time spent revising is controlled, then taking the square of the figure 0.247, we come to know that the variance accounted for is reduced to 6%. Now this is a very low level. That means originally when we were saying that 19.4% variance exists, then that was not exactly the true picture, and the real picture shows us that in fact much lesser relationship intensity is existing, which is 6%, or 6% variance exists in between these variables. So based on this fact, we, while controlling for the third variable, can get the true picture by using partial correlation tool. So coming to this important factor which we just saw, in this case this is pretty much evident that basically initially the variance which was there was 19.4%, and as evident from here, but when we have a look at this relationship while controlling for revision time, then this unique variance is reduced to only 6%. So basically this relationship or partial correlation does give us important information regarding the variance, which is 6% in between them. However, if we had not taken this revision thing into account, then this variation would have been 19.4%. Now, this therefore is very important that we try to get the true picture of the relationship, and in this case partial correlation helps us a lot in getting the true picture. So then this is the scatter plot of various sample data with various coefficient of correlation. So in this case, if let's say we have the correlation R is -1, then in that case our scatter plot should look like this. And similarly, now here if we are observing the R as -0.6, then it should give us a more scattered version of the dots as shown here, and basically all the dots are not exactly on the line, and there is a presence of errors there, so that's why R is -0.6 here. On the other hand, if we take the ideal situation in which R is +1, then we have got exact line of data values which is being portrayed here. But in case of weaker relationship, like with R is +0.3, then in that case you can see that all these data values which are represented by dots are far from the regression line. And in case there is no relationship which exists between these two variables, which would be portrayed by R equal to 0, then in that case we would be facing a straight horizontal line with the data values posted on that. So this basically gives us a brief view of various coefficient of correlation and how the scatter plot would be if it is derived from the sample data. So coming to the next one, what are the main drawbacks in these numerical descriptive measures? You see, data analysis needs to be objective though, but we should report the summary measures, which would give us a detailed overview of an explanation of the data sets. So basically it's not just that you just report the figures and your job is done, but in fact you need to describe and explain all these important aspects of the data analysis of the objective data. Otherwise this objective data without explanation would not make any sense. Then data interpretation is subjective, so it should be done fairly and neutrally without any bias, because this biasness factor plays an important role in getting the study failed in real-time arena. Now data interpretation is always subjective, so that's why it is stated that it shouldn't be done in a biased way, and that's why it's up to the author, and also it's the duty of the author to write that data interpretation in a clear, concise way, and should communicate a real picture in a fair manner. So then there are some ethical considerations as well, and one of them, as you can see, is that we should report all the good and bad results. So it's very much unethical that if your analysis results are not proving something and they are giving negative results which are contrary to your hypothesis, then still it is very vital that you should report them and should not try to manipulate the data. Now, in this case, then also the data should be presented in a fair, objective and neutral manner. So the involvement of the researcher in data collection and in the analysis of data should be minimal in order to create in order to avoid any creation of biasness. And then again, inappropriate summary measures should be avoided to distort the facts. So the facts should be communicated in a very clear and very concise manner, so that there's no biasness involved in that. And these are the ethical guidelines which should be followed while conducting all the analysis. So coming to this, then we deal with another topic which is related to the normal distribution. We have heard this term a number of times, in which numerous times it is said that you have to look at the data and see whether the data is normally distributed or not. Because if the data is not normally distributed, then many statistical tests cannot be applied as it is. So coming to the next one, basically while going through this normal distribution, we are dealing with two variables, which are, one of them is discrete variable and the second is continuous variable. Now in case of discrete variable, these outcomes should come from a counting process. And for example, the example is given to you, the number of classes which you are taking, number of vegetables you are bringing home. Then continuous variable, basically they come from a measurement, and your weight, your salary and other things like that are included in continuous variable. So we are interested more in these type of variables factor in discrete and continuous, but the probability distributions, as these distributions are called, more deal with the continuous probability distribution here, specifically while we are going through studies in business administration. So continuous probability distribution comprises of three important factors. One is normal, the second is uniform, and the third is exponential. So coming to this continuous probability distribution, which is of a more important aspect in business administration, let's have a look at the details. And here in this case you can see that basically continuous probability distribution is a kind of a continuous random variable, and it can assume uncountable values. So various examples you can see here are thickness of an item, items required to complete a task, then temperature of a solution or height, etc. So this type of variable data is considered as continuous random variable, and basically these type of variables can take any type of value which can precisely and accurately give us concise data. So coming to the next part, the normal distribution structure comprises of a bell-shaped curve, and it's symmetrical, and again being symmetrical, its mean, mode and median are equal, but this is the ideal state, not the realistic state. And then location is determined by the mean, mu, which is the location of this central value. Now then again, the spread of the data is determined from standard deviation, and which is also portrayed by sigma. And then again the The random variable basically has an infinite theoretical range, which is stated here. So this is pretty much evident here from this, that normal distribution is of great importance and we cannot just ignore it. Then coming to the density function of normal distribution, the formula is prescribed here, where fx is the any value of continuous variable, which is equivalent to 1 by under root 2, and then there's pi and sigma, and then we have got an error term with an e. So it's also termed as constant. So basically this formula is used to calculate the density function normal distribution. And while going through that, let's have a look at the various parameters which we have obtained from different normal distribution. So this normal distribution density function is only important to calculate the density of the curve. However, the more important thing here is that we do obtain different normal distributions which we have discussed before. Now here A and B both have the same mean but different standard deviation, and again B and C have different means and different standard deviation. So different kind of normal distribution can be obtained, and in this case the standard picture of the diagram is like here, where the central value mu is being nominated for the mean, and again if we keep on changing mu units from distribution from here and there, from right or left, then it would have an impact on the rho. And here the rho basically, the changing rho increases or decreases with the spread. So the more higher the spread, the most higher the rho, and based on that we can calculate the rest of the values and all the entities we are required to find. Now any normal distribution with any mean and standard deviation combination can be transformed into z-score. So in this case the z-score basically gives us the certain value based on the standard deviation, and here to compute these normal probabilities, these need to be transformed from x units into z units, and again the standard normalized distribution z has got a mean of 0 and standard deviation of 1. So this is the standard format, which is a standardized normal in this case. Now coming to this point where we can transform this whole conceptual concept to mathematical formulas. So coming to this, let's say if we translate from x to the standardized normal, then by subtracting the mean of x and dividing by its standard deviation can give us the standardized normal value. So here z distribution has always got a mean of 0 and standard deviation equivalent to 1. Now here the formula is x minus mu divided by rho, and we know what these notations are about, so you can easily go through that. And then coming to the next one is the formula for standardized normal probability density function, which is being represented here. Here you can see the z distribution is represented by a mean which is 0 and its standard deviation is 1, which is shown in the curve. Once it's there, then we can say that the values above the mean have positive z values and the values below the mean have got negative z values. So this is one easy way to calculate the nature of z values from your data set, and based on that, so let's have a look at an example in which a certain value x is distributed normally with mean of $100 and standard deviation of $50. So the z value for x is proved to be 200, but here we can see that z here has been calculated from the conventional formula provided by us, and where x minus mu is divided by sigma, and by simply subtracting 100 from 200 we get the value of z, and that means that x is at 2 standard deviations, which also means that x should be equivalent to 200, and in this case the the mean basically, which is $100, becomes insignificant, and the values reported by standard deviation are of more importance in this case. So coming to the next line, here we are plotting the same information in a bell curve. So you can see here, in this case we have just plotted that example in the form of a diagram, and the values are plotted here with 100 is equivalent to mean, but again if we convert this value into z, the mean would become equal to 0. And here we have also plotted the 200 value, which if we have calculated from z formula has been found to be 2.0. Now here we are being given with the value z, and we have got the value of mu and rho. So the shape of the distribution is a bit changed, but the scale will not change. So we can still express the problem in the original units or in standardized units. Coming to the finding of these probabilities, the concept lies in the fact that the probability of a certain value is measured by calculating the area of curve under that, and from there we can easily calculate the values required, which would give us the probability factor whether we should go ahead with this thing or not. So coming to the details, the total area under the curve is 1.0. So half of the area is above the mean and the other half is below the mean. The reason being so that the basically curve here is symmetrical. So in this case, this is a very ideal case, which normally happens very rare, but here the limits are being given that probability of x, which is less than and equivalent to minus infinity and greater than mu, gives us the probability of 0.5. Likewise, the probability on the other side is also 0.5. So this is the usage of basically the diagram which we discussed before. Now coming to this thing, again we try to find out the cumulative up till z 2.0, which is the z value. Now in order to find that out, we have to find out all the previous activity of the specific study you are going to undertake, and here you can see that the cumulative standardized normal table gives us the probability less than the desired value of z. So basically this is an infinite case, or negative infinity to z. So here you can very much see the probability which has been found out. In this case, the probability required was to be calculated in case the z is less than 2, and here probability tells us how much probability, with how much probability we can assure that this z value is in reality less than 2. So it gives us a vague measure of how to find out a certain probability of a certain figure occurring in the literature. So here you can see that in case that z is less than 2.0, so here we have just basically put the whole thing in red to basically identify the region, basic region which lies behind 2. Now here the region here, the probability while being calculated is equal to 0.9772. So again, coming to the next, how to calculate basically the standardized normal table, how to find out the value of z from the standardized normal table. And here you can see the row here shows the z value to the first decimal point, and then the column here gives us the z value to the second decimal point. So we have just tried to find out the probability from the method which is being easily portrayed in the slide. And here you can see the z value, initial value has been turned out to be 0.9772. So basically this is the way how we use the standardized normal table to calculate the value of z and ultimately to solve our problems. Now again, the grading or the general procedure to find out the normal probabilities is easy. First you draw the normal curve for the problem in terms of x. Then you translate the x values into z values. Now these z values can be easily calculated from the formula we discussed before. And then we use the standardized normal table in order to calculate the z value which is required. So here basically again we are taking another example in which x is supposed to be normal with the mean of 18 seconds and the standard deviation of 5 seconds here. So we are asked to find out the probability, whether how much probability is there that the values will lie in below 18.6. So here we have just drawn the diagram which is evident here, and from here you can see basically the 18.0 which is being presented as the mean, and 18.6 is a little bit ahead of that mean, and from where we can easily draw the diagram. And then while we have covered the previous area in order to find out the probability, we have to first find out the z value, and here in order to do that we just applied the formula which is z is equal to x minus mu divided by sigma. So here all the values x and mu are 18.6 which are presented here. Mu sigma here is represented by 5, which is a standard deviation, and once we calculate that we see that this graph then portrays us the real picture, and here in reality the probability of value of z less than 18.6 has been calculated, which is portrayed here. So these are various methods which are commonly used to calculate the normal probability, which is very much important while specifically evaluating the significant level of the test. So here again another example, we have to find the value of probability while z is less than 0.12. Now we already know how to find the value of Z from the table, and which is again the standardized normal probability table, and its value can be found out, which happens to be 0.5478. So once we have gone through that, the probability can easily be calculated. So here again, now here the example is a bit different, because here we are now trying to find a probability for the value of x which are greater than 18.6. So we have shaded this area in order to highlight the value, and first, in order to find that out, we just try to find out, we know that the total probability area is 1. So if 0.12 is the probability of a certain region, then we have tried to calculate the opposite region probability, and by subtracting the relevant values we are able to calculate the required probability value, which is vital here. So this is the end of how we go through the probability of how we find the probability of various values occurring at a certain range. So in this case, I hope you understand this thing. So in today's lecture, we went through how to calculate the coefficient of correlation in SPSS, and how to basically interpret its application there. Then we went through the partial correlation, why it's used, and we basically took a practical example and tried to find out the partial correlation of certain entities. Once we went through that, we discussed the ethical consideration of analyzing the data and what biases should the researcher avoid. Once these ethical considerations are taken into view, the research study becomes quite neutral and fair in this case. Then we had an overview of what's a normal distribution and how to calculate the value of Z, and how to calculate the probability of a certain value of Z occurring in a certain area. So these were the things which were generally discussed today. Thank you so much. Allah Hafiz.